Welcome to this explainer. Okay, so if you've ever stared at a 3 by 3 matrix and felt this immediate knot in your stomach, trust me, you are absolutely in the right place. Today, we're unpacking a method that literally takes linear algebra from being this abstract equation-heavy nightmare and turns it into a super intuitive 3D visual journey.
Seriously, just think about this for a second. Why do we spend hours and hours memorizing these rigid matrix formulas when we could literally just draw them? For anyone battling with the abstract rules of linear algebra, you know the struggle is totally valid. Textbooks tend to make it completely unintuitive, but what we're looking at today offers a direct, visual solution that basically bypasses all that rote memorization.
Let's just compare our options here. Traditional algebra forces you down this very specific, tedious path where you have to solve complex equations, like setting the determinant of a minus ri to 0. It's heavily abstract and, let's be real, incredibly prone to calculation errors. But our geometric shortcut? It's profoundly simple. We're literally just finding where planes intersect using basic cross products. It's like a secret shortcut hiding right in plain sight.
So here's our roadmap for this explainer. First, we'll look at the traditional math problem. Then we'll jump into the geometric shortcut. After that, we'll see how rank actually shapes the space, visualize a few scenarios, and finally wrap up with some validation and code.
All right, part 1, the traditional math problem, a cognitive overload. If you think back to your standard textbook approach for finding an eigenvector, it is quite frankly just massive cognitive overhead.
The pain points of that standard method are so real. It relies completely on solving that determinant equation. And once you finally have a root, you have to plug it back in and solve these 3 variable simultaneous equations. And oh man, when you hit repeated roots, it is incredibly easy to drop a negative sign or make some basic arithmetic error that throws off your entire answer. Worst of all, it relies on blind memorization rather than actual spatial understanding. You're just crunching numbers without really seeing what they mean.
Moving right along to part 2, the geometric shortcut, changing your perspective. Let's completely pivot away from that algebraic pain for a second and look at what a matrix actually is. Going through the source material, here is the huge aha moment. Take a look at the standard equation. A minus ri times x equals 0. Stop treating it like an abstract string of variables. Instead, imagine it geometrically. Every single row of that resulting matrix represents a flat plane. We're simply looking at 3 literal planes floating in 3D space, and they all pass right through the origin.
Okay, on to part 3, rank shaping space. To figure out exactly how these 3 planes interact, we need to introduce a crucial concept that acts kind of like a geometric sorting hat. And that concept is rank. Think of rank as an indicator of just how much our 3D space gets squished or compressed by the matrix. If the rank is 3, the space is uncompressed. A rank of 2 means the space has been squished flat into a 2D plane. Rank 1 means it's compressed all the way down into a single 1D line. And rank 0? That means it's completely collapsed down into a single point right at the origin.
And this brilliantly illustrates our little mental cheat sheet for eigenvectors. When the matrix rank is 2, our 3 planes intersect perfectly at a specific line. When the rank is 1, those planes are squished so hard they perfectly overlap into a single flat sheet. And when the rank is 0, well, we have a 0 matrix, meaning there are absolutely no constraints at all, and the entire full space is wide open to us.
Which brings us to part 4, visualizing the scenarios. Let's actually picture what these specific situations look like and see how we can extract our answers directly from the geometry itself.
So the crucial takeaway for a rank 2 scenario is this. Imagine 3 planes intersecting, kind of like the pages of a half-open book. That middle spine where all those pages meet, that intersection line is exactly what we're looking for. To find it mathematically, you just take 2 non-parallel normal vectors from those planes and calculate their cross product. Using the right-hand rule, the resulting vector shoots perfectly down that intersection line. And boom, that is your eigenvector. Now let's move to rank 1 and see how this builds. Here, the space is even more compressed. The planes are stacked perfectly on top of each other, completely overlapping like a single flat sheet of paper. Since any vector on this flat plane works as an answer, we simply extract 1 normal vector from the plane and use cross products to generate 2 independent orthogonal unit vectors. Those 2 vectors form the base to describe our flat eigenvector space. And then we have rank 0. This is honestly the simplest scenario, where the math basically just throws its hands up and gives up. The matrix is entirely zeros. There are no planes, absolutely no constraints. This means that literally every single direction in the entire 3D space is an eigenvector. Your standard x, y, and z axes will do just fine here.
Finally, part 5, validation and intuition through code. It's one thing to casually draw these concepts out on paper, but we need to prove that this visual shortcut actually holds up against rigorous mathematical software.
If we look at the code from our source material, we can see this program replicates our exact geometric method. Notice how it breaks everything down? It doesn't use obscure black box algorithms. It uses basic high school level tools, mapping out functions, using the Saurus rule to find determinants, and simple right-hand rules for cross products. It literally turns abstract algebra into explicit geometric actions. So how do we know our visual method is perfectly accurate? Well, the algorithm checks its hand-calculated geometric work against heavy-duty libraries like NumPy. For rank 2 lines, it uses dot products. If the result is nearly exactly positive or -1, our intersection line matches their algebraic output. For rank 1 planes, it mathematically checks if our 2 chosen basis vectors span the exact same subspace as the standard software's output. It is perfectly validated spatial logic.
So, what's the ultimate takeaway here? It's simple, really, and it's incredibly empowering. You do not need to be a math genius to find an eigenvector. You don't need to get lost in a terrifying sea of simultaneous equations and repeated roots. You just need to change your perspective and look at where the planes cross in 3D space.
The author of the source material left us with this profound concluding thought, and honestly, I think it summarizes everything perfectly. The moment you see the plane intersection, you've found the eigenvector. Take a second and let the beautiful simplicity of that geometric realization really sink in. It completely demystifies the matrix.
Once you start learning visually, you kind of can't really go back. So I want to leave you with this thought. Now that you can literally visualize and see an eigenvector right in front of you, what other intimidating, complex math concepts are just waiting to be drawn out? I highly encourage you to look for the visual geometry hiding in all of your future equations. Thanks for joining me for this explainer, and keep exploring.